Good evening, everyone. On behalf of ASCE Geo Institute, this is Michael McNicholas, the chair of the committee for this year. I want to thank everybody for signing on to the webinar this evening. We really were excited about this lecture, and we really wanted to broadcast it to everybody. And I want to give a thank you right off the beginning for Willie Nesmith and also all the members from DFI for helping us make this happen. It was a lot of behind the scenes work, so I give my gratitude to you guys right off the bat. I want to welcome everyone to the 6th annual RA lecture sponsored by RA Engineering. RA Engineering has been a proud member and representative of this committee and also ASCE. They were founded in 1991 and practice primarily in New York City and the metropolitan area. As shown on the slide right here, they're involved in a lot of the subsurface investigations and deep foundation design throughout New York. And we want to thank Nadal and Company for being a sponsor for many years in the past and for years to come throughout the lecture series that we have. Just want to remind everybody of the upcoming events that we have from our lecture series calendar. We have one remaining lecture, will be the 18th annual William Barclay Parsons lecture on April 15th. It will be done by Ray Castilli, and he is going to be speaking towards current topics in excavation support. And also please keep an eye out on emails. We'll be reaching out to everybody about our 44th annual one-day May seminar. Currently it's going to hold at the May 7th date at Hotel Penn. Again, our topic is 100 years of complex underground infrastructure, challenges and breakthroughs. The authors have been working very hard on their papers, and from the preliminary ones I've looked at thus far, it's going to be another great event for us. Again, I just want to make a quick announcement about our graduate scholarship that we offer for people that are pursuing a geotechnical degree in the New York City metropolitan area. Please get your applications in. You can send them directly to me or any other of the members that you know are on the Geo Institute committee. I do finally want to thank all the members of the committee that have worked very hard this year. We can't do all these events without the volunteer dedication of all these individuals. They really work hard behind the scenes, and especially for this session here, we've really focused to try and bring this structure and lecture series to you guys this evening. The way that you're going to receive your certificate is everybody that has pre-registered has provided their name, first and last, and also an email address. Once we get after the seminar, we're going to have everybody's email, and we're going to send out one blanket certificate for everybody so you can have it in hand at the conclusion of just give us a couple days to get through the technical side of it. But this is a PDH accredited presentation that we're going to have. Finally, in addition to silencing your cell phones, just try and keep yourselves on mute. The way that we're going to handle questions is there's a question prompt that you have on the side of your GoToWebinar screen. Willie's going to stop at occasional points, and I will facilitate any questions that come from the audience. Otherwise, we'll have questions at the conclusion like we normally do. Without further ado, I want to introduce and give the floor to Mr. Willie Nesmith, the DFI traveling lecturer, and the application of drill displacement elements for liquefaction, mitigation, and foundation improvement. Willie, I want to thank you for making this into a webinar, and I will give the floor to you, sir.
Thank you very much, Mike. I appreciate being part of the program tonight, although I was looking forward to spending a couple of days in the city. I haven't been to the city in a while and haven't given a presentation in New York for maybe 10 years, but this is the way it worked out, and that's fine. Just to share some regional information with you on the virus situation. I live in South Georgia, about 45 minutes outside of Savannah, and in this area, there are a lot of home remedies and that kind of thing. And early in when we got the news of the virus, the word around the campfire was that you could stave off the virus or at least mitigate its effects by drinking a large amount of alcohol. And I will have to tell you right now, that has worked very well for me. Just some anecdotal information to pass on to you for what it's worth. Many times in my career, I have come across the term emeritus, and I always thought it was a grand sounding term. So when it was applied to me, I enlisted the help of someone who had taken Latin in high school to try to determine what it really meant. And what they told me was, it literally means an old person who is not paid. And so after 45 plus years of dedicated service to the geotechnical industry, that is what I have come to. As Mike mentioned, this lecture is part of the traveling lecture series put on by the Deep Foundation Institute. It is the fourth of 7 lectures that are to be given. And as I have traveled around literally from coast to coast, I've been surprised by the number of people who don't even know that DFI exists or don't really know what the DFI is. So I thought I'd take a few minutes to discuss that. And actually, in terms of my own experience, the DFI was formed in 1976, a year after I graduated from undergraduate school. And for the following 20-ish years, I worked as a geotechnical consultant. And quite frankly, I didn't know what the DFI was. In the latter part of my consulting career, I sort of gravitated toward working for deep foundation contractors and ultimately went to work for Berkeley Company contractors in the late 90s. And it was only then that I got involved in the DFI. And what I found was these are the people that I have been needing to talk to for the past 10 or 15 years. The DFI is made up of about a third of the membership is contractors, about a quarter consulting engineers, and then there are suppliers, academics, and owners. But what I found was this was a place for the people who design and who construct geotechnical construction come together and talk about things and learn about each other and really solve problems. As probably most of you know, solving an issue in the heat of construction out in the field is maybe not the best place to get things done. So at the DFI, the people who conceive of the project and the people who make it come to fruition can come together and discuss issues. And I wish I had come up with this, find common ground. I think that's just terribly clever, but it really is the essence of what happens at the DFI. This is a list of the committees that are currently active in the DFI. The two that are highlighted in red are simply highlighted because they're the two newest committees that have been formed. But if you're interested in any aspect of geoconstruction, there is a committee at the DFI for you to get involved in, and a lot of people for you to talk to. Upcoming programs in the DFI, actually the international conference in late March has been postponed, but as far as I know, the rest of these conferences are still on the schedule. I would particularly recommend to you SuperPile 20. This is a yearly program that moves between major cities and is focused particularly on pile foundations. So if you're into piles or geoconstructions of any sort, I have found that to be a very useful program. The DFI National Conference this year is going to be held in National Harbor, Maryland in October. So if you want to look into DFI or want to find out more information, go to dfi.org and perhaps you can find common ground with someone in the organization. This evening's program is basically a discussion of the use of displacement elements for liquefaction mitigation and foundation improvement. And the scope of the presentation is the evolution of drill displacement pile operations, a discussion of the installation platform, the tooling, and you can see the abbreviation there, CGE, that's for cast in place ground improvement element, and I may use that from time to time. The installation method and automated monitoring that's involved, the improvement from installation, and then a couple of case histories. I think it is of value to take a look at drill displacement operations versus conventional auger operations, and it's represented well by this drawing that was taken from the transportation research record. So conventional auger cast in place pile operations got their start in the late 1940s at a company called Intrusion Prepack. And that company primarily did compaction grouting. Occasionally, in order to get their grout pipe down to the level that they needed it, they would use a solid auger to penetrate some hard material. Then they would drive a grout pipe beside the auger and then extract the auger as they were grouting. And somewhere along the line, and I never could get a straight answer from Mr. Burkle as to who came up with this, they decided that if they turned all their tooling sort of vertical, they could actually build a cast in place pile. And an amazing number of structures, particularly in the Midwest, were constructed using this process, a solid auger with an auger pipe driven in beside it. At about the same time in Europe, they were working on what was called a screw pile. And that's illustrated by this screw on the right. And their emphasis was on extending the tooling into the ground while removing as little material as possible and focusing on the drilling operation. These screw piles were typically cast with very, very plastic concrete. It had a lost shoe on the bottom. So as the tooling was withdrawn, the tooling acted as a trimmy, and concrete filled the void that had been created by the tooling. So these two systems were developed at about the same time, that they were fairly drastically different in concept. On the US side, the idea was to make a hole in the ground quickly, remove all the material that was in the area of the pile, and then cast the pile with fluid grout. On the European side, the emphasis was on drilling while at least maintaining the state of stresses that were in the ground and hopefully improving them, and then casting the pile with very plastic concrete. So right off the bat, the concepts for these two systems were very different, and they evolved quite differently. So in 1985, an engineer named Gaspar Coelius was granted a patent for a full displacement pile. Now, this engineer Coelius had in the previous decade been granted a patent for a screw pile, which was a continuous flight pile, and I'll talk about that a little bit later. But Coelius's full displacement pile had a section of conventional auger and then a ramp up to a displacement body, some reverse flighting, and then a stem that was smaller than the tooling below it. It was advanced into the ground where possible. It was advanced like a screw in that it did not bring up any material. In denser material, some of the soil may have been transferred up, but it was ultimately pushed to the side by this displacing body. When they got to the point of termination, the tooling was withdrawn, leaving the lost shoe in place, as can be seen here. And then ultimately, reinforcing steel was placed in that plastic concrete. The first European displacement systems came to the United States, as far as I know, in the early 1990s. And they were installed with rigs like the one you see on your screen now, which is a fixed mast rig. Quite different from the crawler crane mounted rigs that were used to install conventional auger cast in place piles. They had a turntable at the top, which was capable of producing very high torque, a stem that ultimately served as a conduit for the concrete or grout. In addition, one of the things that came over with the European rigs was the ability to gather a lot of information on the drilling side of the process. As I said, the emphasis on the screw piles was on the drilling. And again, contrast that to conventional auger piles where there's little emphasis on the drilling. You simply make a hole as quickly as you can. Then the emphasis is on the filling with fluid grout. But these rigs came over with the ability to monitor the rotations of the rig, a main winch proximity switch, which could determine depth, a pressure sensor on the motors that were driving the turntable so that you could monitor the pressure of the turntables, which is sort of related to torque, and an inclinometer. And this is incorrect. The inclinometer is mounted in the fixed mast, not in the tooling. But basically, these rigs showed up in the United States from a displacement pile installation standpoint in the early 1990s, and it began what has ultimately turned into a melding, if you would, of the European and the U.S. Systems. This photograph was taken at a project which was part of a redevelopment of the old Howard Hughes Airport in Los Angeles County, and it was the first cast-in-place pile system that had been used in Los Angeles County. And as part of the approval process, Burkle was asked to exhume a pile so that the regulatory agencies could look at it. And there is the pile, and all that water was a result of the jetting process that it took to exhume that pile. And it was quite expensive and quite troublesome, actually. But in the end, it turned out well because it helps illustrate one of the benefits of cast-in-place piles. And you can see the upper part of this pile went through a silty sand, sandy silt, and the lower, approximately 3 feet, was in coarse sand and gravel. And you can see how the pile, there is no smooth pile interface here. The grout actually penetrates into the sand, and the removal or the elimination of that smooth interface really help develop shaft resistance in these piles. And that is one of the benefits of cast-in-place piles in general. Again, these installation platforms are developing very, very rapidly. And at the current time, you can find torques of the driving heads of 150,000, 200,000 plus foot-pounds, 40 to 80,000 foot-pounds of crowd, which is downward force on the tooling, a fixed mast for stability. On the Burkle rigs, there is a pressure sensor here. Burkle uses fluid grout to cast its piles, so the pressure sensor is used to monitor the pressure of the grout. A real-time display of some installation parameters, including depth. KDK is the pressure of the fluid pressure of the motors that are driving the turntable. And you will hear me wrongly refer to that as torque. It's not really torque. It can be related to torque, but it's the fluid pressure of the motors driving the turntable. Installation effort, which is a term that I'm going to discuss later, and grout pressure. The displacement system that I'm most familiar with, because I work for Burkle, is the Burkle system. It again contains about 3 feet of regular flighting. Then as you move up the flighting, the stem becomes progressively larger and terminates in a displacing element, which is the same size as the tooling below it. Above the displacing element is some reverse flighting, and then a stem that is smaller than all the tooling below it. The installation method looks very similar to the one that I described for the Coelius pile. You drill down, the tooling penetrates like a screw in loose to medium material. If dense material is encountered, there is a transport of material up the tooling, and then it is forced out to the side by the displacing element. When the termination level is reached, grout is pumped. The grout pressure is monitored by the operator. Again, remember the pressure transducer is mounted on the top of the tooling, and he can see when the system is pressurized. And when it is, he begins to lift off, and the tool is rotated as it comes out so that any material which may have fallen into this annular space around the stem is pushed out to the side and ultimately displaced. One of the differences between displacement pile systems and conventional auger piles is you typically only get a grout return after the tip is at or near the surface, so that the pressure of the soil here is no longer able to withstand the pressure of the grout that's in this column, and grout squirts up by the side and enters the surface. So you don't get a head of grout as you might expect to get in a conventional auger pile operation. This is a photograph of the Burkle displacement pile tool. There is the grout port. This was from a calibration process. There's the grout port. There's the cork that was blown out of the grout port, and there is the grout, which is typically a thick milkshake consistency. I want to discuss an intermediate or partial displacement pile system, and this system, in fact, is much like the original European screw pile system. To compare the tooling, this is conventional auger piling tooling. This is the drill displacement tooling we just talked about. And this in the center is the intermediate displacement pile tooling. You can see that the center of this tooling is very large in comparison to the flighting. And again, this is very much like the screw pile tooling that was part of the original screw pile development in Europe. A photograph of conventional auger tooling here. You can see a relatively small tooling, API threads, large flighting. This is partial displacement tooling, you know, a relatively small flighting in terms of the diameter of the stem. And right here is a problem. This particular piece of stem got stuck in the ground and the grout hardened, and somebody is going to have to go out and drill that piece of tooling out and remove that grout. But again, just a comparison of the heftiness, if you will, of the intermediate or partial displacement tooling versus conventional auger tooling. A man named Vigiani from the University of Naples came up with this equation, and what he was expressing numerically is what you would come up with intuitively in terms of what you wanted to do with a screw pile or a partial displacement pile, and that is make the stem as large as you can relative to the diameter of the flighting, and then make that tooling penetrate at a rate ideally which was equal to the rotational speed times the pitch, which is expressed here. The key element is in order to get net compression, the displaced volume must exceed the removed volume. In other words, you need to displace more than you remove from the hole. And this was the essence of the screw pile approach, and is an important element in the intermediate, or what's now called in the US, partial displacement approach. So we've looked at two different displacement operations, one full displacement, one partial displacement. So the partial displacement would come into play when there were strata that needed to be penetrated that could not be penetrated by full displacement because they were too dense, but yet had areas in the profile that could benefit from displacement. So the partial displacement system or intermediate displacement system you use the same installation platform as drill displacement, high torque, high crowd, fixed mass system, a large stem and small flighting. And at Berkel, that flighting is typically less than 1.5 inches, and the stem may be 10 to 12 inches in diameter. The tooling is screwed into the ground where possible. You get displacement. It is drilled into the ground where it is necessary to excavate. But again, the goal is to excavate as little material as possible. The idea is to improve loose soils and limit stress relief in dense soils. The target spoil volume is less than that of the neat hole. And we, early in the use of this system, we actually measured the amount of spoil. We scooped it up and packed it down and attempted to measure on a real volumetric basis how much we were taking out of the pile volume to make sure that we were getting less material out than the volume of the pile. These piles are sometimes cast like auger cast in place piles by volume. or they may be cast by pressure, like more like drill displacement piles. So, in summary, the benefits of cast-in-place displacement systems: minimal spoils, no vibration, low noise, easy to vary lengths to suit the site conditions. And actually, these three, the noise, the vibration, and the variability in length, are common to all cast-in-place piling systems. But the minimal spoils and the improvement in soils that are responsive to displacement are particular to the displacement systems. So early in the use of the displacement system, and it was being used primarily as a piling system in the late 90s and right after the turn of the century, it became obvious that as we continued to put this tool in the ground, the material got more dense if we were working primarily in granular materials. So an early attempt to quantify what that level of improvement was a project in South Florida where we had a typical test pile set up, 4 reaction piles, test pile in the middle. And we came outside of that setup and created a symmetrical 4-pile cap spaced at 4 diameters. We then came in and did a CPT in the center of that cap that we had created, and then started doing CPTs at 1 diameter intervals away from one of the exterior piles. And the idea was to find out at what point there was no discernible increase in density away from the pile. As luck would have it, we had an equipment failure, so we only got to this point 3 diameters away from the pile. So we used the information from 3 diameters away from the pile as the ambient condition. So this is the ambient condition. Again, this is what we found 3 diameters away from the pile. The area of interest was between about 10 and 25 feet below the surface, which was a fine sand with a trace to some silt, and then with some occasional clay and silt layers. And the average cone tip resistance in that zone was 32 TSF. This is a plot of the information for the cones at 3 diameters away, the red trace, 2 diameters away, the blue trace, and 1 diameter away, the black trace. And what we found was taking what we then thought was we had to use as our ambient condition, we go from 32 TSF to 68 TSF to 84 TSF at 3 diameters away from the pile. We later learned that the discernible distance at which you can tell if displacement is changing the density of the soil is between 4 or 5 diameters from the pile. But again, this was an early attempt somewhere in the early 90s, I think, at trying to figure out what the level of increase in density was in granular material adjacent to displacement piles. For the CPT in the center of that 4-pile group we created, again, this red trace is the ambient condition. The black trace is the CPT in the center of the 4-pile group. So what we found was in the center of that group, we had about a 3-fold plus increase in cone tip resistance in that sand zone after the installation of in the center of what would be a 4-pile group spaced at 4 diameters. After we did that operation that I just described, it became clear that there were possibilities to use this system as a ground improvement tool, as well as a piling system. And so we embarked on a bit more ambitious testing program, looking at a variety of configurations. And that information is published in 2007. It was also published in an ASCE publication, but it basically laid the groundwork for an area replacement ratio type approach to ground improvement using the displacement system. So in summary, what we found was when displacement elements are installed in materials that exhibit granular behavior, there's an increase in material density in the vicinity of the piles. It extends to about 4 or 5 diameters away from the pile. The increase is most pronounced in loose to medium dense materials. As the in situ density increases, the percentage of increase in density decreases, and there was no discernible increase when that tooling was extended into dense granular material, basically somewhere around an N value of 30. And the fact of the matter is it becomes extremely difficult to extend the full displacement tooling into materials with a standard penetration resistance in excess of 30. We found that the increase in density is additive. That is, the more elements that are installed, the greater the level of increase. And as a result of that program I just described, we came up with a design process to develop a configuration, size, and spacing to achieve the desired level of density for a variety of soil types. I'm going to stop for a moment now to see if there are any questions at this process. If there are not, I will continue on.
Willie, we have 2 questions that came in. The first question reads, as with conventional auger cast in place piles, is there a requirement for installing a minimum amount of grout at the bottom of the displacement pile?
For the Burkle displacement pile, well, let me speak to both all right, at the present time, there are systems out there in the United States which use what I described as the Coelius displacement pile, which is cast using a lost shoe and fluid or very plastic concrete. Okay, so when they get to the termination level, that stem is filled with concrete, and then the tooling is lifted. And In a lot of cases, there is a guy sitting in a basket up top looking down at the tooling, making sure that the concrete level relative to the top of the tooling drops. In other words, that the concrete drops. So that the Coelius system with the lost shoe is a gravity system. It's just like a Tremie system for drill shafts. The Burkle system, which uses fluid grout, there is no requirement for a certain number of strokes to be pumped before the tooling is lifted. The requirement, what is happening is the operator is observing the grout pressure, and recall that that grout pressure is measured at the top of the tooling. So whatever that grout pressure is the pressure at the top of the tooling. So you have to add in the column of grout from the top of the tooling down to the bottom, which can be 60 or 80, 90 PSI. So the liftoff with the Burkle system using pressurized grout is governed by the operator seeing that the system is pressurized. So I believe the question is there some number of strokes or volume of grout that must be placed? And the answer is no. But if you checked it, you would find out that the volume pumped is about equal to that to fill the stem and start to pressurize the system.
Excellent, thank you. And the second question, it was actually a second part of the question, which I think you covered in that response, was, is there a minimum grout pressure required during the displacement pile building of it? So I believe you answered that to the person asking the question satisfaction. That's all the questions we have at this point, so you can continue on.
Okay, thank you. So then it comes to what soils exhibit granular behavior. And on one end, it's very easy. Okay, sands, clean sands, no problem. But at some point, as you continue to add fines, the ability to densify soils starts to diminish, and that's because they become no longer free draining. And so if they're not free draining, you don't densify them by the passage of this tooling in the ground. So I took this from a 2003 paper that I did that ultimately became part of the displacement discussion in GEC 8. And somewhere around 40% passing the 200, the displacement process starts to get a little bit dicey. And again, it's because the materials are not free draining and they, just don't densify by the passage of the material. So the answer to the question is exhibit granular behavior, clean sands up to the point where you get about 40% passing the 200, and then it begins to get a little dicey. If you're doing CPT work, piezochome work, anything that exhibits a pore pressure response is going to be a bit dicey because, again, you need this material to be free draining in order for it to densify. Early in my work with this system in terms of mitigating liquefaction, I was under the misguided conception that if something graded out as liquefiable, then it should be densifiable by the displacement system. And again, I admit that was misguided. And what brought me back to reality was saturated silts. And the fact of the matter is, saturated silts in general do not respond very well to displacement. And in one of the case histories later, I will show you that. But again, in terms of materials that you can depend on to densify with the passage of the displacement tool, clean sands up to about 40% fines. At that point, it becomes a little bit dicey. Saturated silts, I wouldn't count on it. My heart has been broken several times by trying to densify saturated silts. As I mentioned early in the presentation, one of the things that came over with the fixed mast equipment from Europe, or one set of things that came over, was the ability to gather a great deal of information about what was going on the drilling side of the operation. Recall auger cast in place piling, they didn't really pay much attention to what was happening on the drilling side. Everything was focused on the casting side and providing an oversupply of grout, which assured a complete pile. The European system was all about monitoring the drilling side of the operation, and with that came the ability to easily monitor a number of things on the drilling side of the operation: time, depth, hydraulic fluid pressure driving the turntables, again, KDK, which I'm undoubtedly am going to refer to as torque at some point, and rotations of the turntable. In the European screw pile system, they had used the hydraulic pressure that was driving all of the equipment. They had used that as sort of an indicator of the kind of material that was being penetrated. Obviously, the material was more dense. The hydraulic pressure would have to kick up in order to penetrate that. So even in the European screw pile system, they had already began to look at KDK pressure, or hydraulic fluid pressure, as an indicator of what was being penetrated. And this is a fairly straightforward record of an installation process. This is with a full displacement pile. This chart shows a trace of the parameters: KDK pressure, hydraulic pressure, depth, and grout pressure with time. And down in this portion, those parameters are shown with respect to depth. This is the penetration depth. This is the withdrawal process. This is KDK pressure, again, hydraulic pressure to the motors driving the turntable. And this is grout pressure in casting. This parameter is installation effort. And what this parameter seeks to do or the reason for developing this parameter was to attempt to show a picture of the profile as the pile was being developed. The red trace here is cumulative installation effort, which is basically an integration of this black curve, and it can be related to total pile capacity. So in order to try to paint this picture of stratigraphy that was being penetrated, we came up with the concept of incremental installation effort. And again, it was an attempt to show what was being penetrated in a real-time sense, and in order to provide a record for what was being penetrated. On the left is a trace of a CPT that was done at a pile location, and then the other parameters are from a pile drilled at that CPT location. The first parameter is torque. Again, it's not really torque, it's fluid pressure of the motors driving the turntable, and then the penetration rate. And so you can see, just looking at fluid pressure of the motors driving the turntable gives you somewhat of a picture of the stratigraphy as indicated by the CPT. But what we found was that different operators with different techniques could kind of skew this thing if they put more crowd on the tooling, they could kick the fluid pressure up. So we also saw that if they crowded the tooling in material that wasn't very resistant, the penetration rate went up. So we combined fluid pressure and penetration rate inversely to come up with this concept of installation effort. And again, the only reason for this existing was to allow for a picture of the stratigraphy to be seen while the element was being drilled, and also to provide a permanent record of what was being penetrated. And you can see that this incremental installation effort trace looks a good bit like the CPT. I was asked early on, okay, you did that once, but what about repeatability? So these are the records from 4 reaction piles at a test pile setup. And you can see that the first thing wasn't just a fluke, that you do get a good representation of stratigraphy, or a repeatable representation of stratigraphy from this system. This slide shows what the operator sees and what can be seen on a laptop or a cell phone. Actually, as the pile is being driven, the installation, the tool penetration on the way down, tool penetration on the way up, the fluid pressure, and then the incremental and cumulative installation rates. So if you want to look into this installation effort business a little bit more, it was discussed in excruciating detail in a series of papers. The first paper was at the BAP conference in 2003, and then in 2006, a couple of papers on the use of the information acquired that can be developed from the installation of these displacement piles. The first case history that I wanted to look at was in Woodbridge, New Jersey, a combined cycle gas-powered generating plant. It was not a liquefaction mitigation. It was a ground improvement system where we were looking to improve conditions to the point that mat foundations or shallow foundations could be used for these elements. This is a layout of the displacement elements that were installed. The idea was to install a system that would allow foundation bearing pressures of from 3,000 to 4,200 PSF. The kicker on this site was it was highly contaminated. The material in the fill in this uncontrolled fill and loose to medium sand was highly contaminated. There was a dense sand as the basal layer, and then saprolite below that. So the charge was to improve, stiffen the uncontrolled fill, improve the loose to medium silt and sand, get the toe into the dense sand, but not dare penetrate down to the saprolite because of the contamination that was up in this zone. The undulation of this dense sand was a little bit more than is implied in this picture. It was actually, it varied by 10 to 12 feet. So making sure we penetrated the loose to medium silt and sand and got into the dense sand, but yet only just touched it and did not penetrate the dense sand was a critical item. So we used the data collection system that I described previously, in particular the cumulative installation effort, this black trace, as an indicator of when we got into the dense sand. Again, we only wanted to go in deep enough to verify that we had hit it. And this incremental installation effort process turned out to be an excellent tool for doing that. You can see where it kicks up. This is the fluid pressure trace. You can also see that it has a kick there, but the installation effort portion was much more distinct. And again, it was critical that we get to that lower sand, but not penetrate it. So that system worked well in that environment. And those elements varied in depth from 25 to 35 feet. So if we had set a level target, we could have been too deep in some cases and not deep enough in others. So liquefaction, probably everybody listening to this program understands, at least in concept, what liquefaction is. It occurs normally in loose granular sediment or fill. There's saturated by groundwater, and then there is some strong shaking, most often by earthquake. So the most common way to attack this situation is to try to improve the loose granular sediment or fill to the point where we have a factor of safety relative to liquefaction in excess of 1. The project that I'm going to talk about is a hospital in Owensboro, Kentucky. It had a 9-story tower, a 5-story medical office building, column loads ranging from 300 to 900 kips. The design earthquake was 7.5. The design acceleration was 0.26. We had generally about 30 feet of soft clay and silt underlain by loose to medium sand to a depth of 50 feet, and both the silt portion of the upper 30 feet and the sand from 30 to 50 feet were considered to be subject to liquefaction. So the design approach here, based on the charts that we had developed, was to install 7,500 16-inch diameter by 50-foot elements at a spacing of 8 feet center to center. That was a triangular spacing in the building area to mitigate liquefaction in the lower sand. We adjusted that spacing to align with the orientation of the footings so that we got a symmetrical spacing around the footings, and I'll show you an example of that later. Then we also installed an additional 1,700 16-inch by 35-foot diameter shafts in the footing areas to reinforce the soft silts. Ultimately designed for shallow foundations for an allowable bearing pressure of 6,000 PSF. And a real key item was, based on this improvement process, we moved from a Class F to a Class D, which resulted in some significant redesign and savings in the superstructure. This was a general test area array. This is a 7-foot triangular spacing. This is an 8-foot triangular spacing. We knew that we were going to need supplementary elements within the footings, so these cones before and after gave us an indication of what kind of level of improvement we could get. We did an actual plate load test with a 10 by 10 plate. This is the configuration with the in the plate load test area. Again, the primary triangular 8-foot spacing, and then the intermediate spacing. The test was done with 16-inch diameter elements, and these intermediate elements were 12-inch. What we later found was that the 12-inch elements were too easily broken during the excavation of these things. So we ultimately moved to 16-inch elements for the primary liquefaction mitigation, and the secondary elements that were needed in the foundation areas to reinforce those silts. We did a series of load tests. One was a 10 by 10 plate load test. We designed and built a frame to run this load test with. Again, we did, I think, 4 load tests like this. There were some variation in conditions across the site. Basically found that the movement in the plate load test was acceptable for what we needed. We did, actually, Dan Brown and Associates was our consultant on this, and they wanted to see some modulus tests, so we did those using the installation platform as reaction, but that was a modulus test and an example of the result that we got from that test. In the end, what we found was we did a really good job of moving the sand that existed from 30 to 40 feet into a position where the factor of safety was greater than 1. And this, again, was another heartbreak area. because the silts that show as liquefiable did not respond to displacement. And so we're still over in the had a factor of safety of less than 1 against liquefaction. So the extra elements that we put in the foundation area were not only to reinforce the silts, clays and silts from a settlement standpoint, but to boost the level of confidence for materials in this upper 30 feet that showed a factor of safety of less than 1 in an earthquake situation. And this was the predominant paper that we relied upon at the time in terms of reinforcing this area of silts and clays rather than improving it. And this is just an example of what we did for each footing location in terms of our primary spacing, which was the open circles, and then the secondary CGEs, which are the closed spacing. Again, we ultimately went to all 16-inch elements simply because the 12-inch elements were too delicate to for the excavation operation. We did use the installation effort concept when we were putting in the shorter elements, just to verify for us that we were reaching the lower sand. And you can see here again where the installation effort trace kicks out at about 30 feet, but there was some variation in that lower sand. The last project that I wanted to talk about, I wanted to look at simply because we used shear wave velocity rather than tip resistance as our measuring stick for liquefaction mitigation. You can see here the shear wave velocity before was kind of rambled around 250 feet per second or less. We basically gave the contractor an option of dense graded aggregate or a mud mat sitting above these elements for the mat foundation. And this is the shear wave velocity trace after, and then this is a comparison of shear wave velocity before and after installation of the displacement elements. I think I'm getting close to the end of the allotted time, if I haven't gone over. Mike, do we have time for questions, or do we have questions?
We absolutely have time for questions. One question came in when I believe you were talking about the Owensboro Hospital in Kentucky. And the question reads, were footings checked structurally when using drilled displacement piles?
Okay, say you're a little bit garbled, so please say that again, please.
The question came in while you were talking about the Owensboro Hospital, the work that was done there.
Yes.
And it reads, were footings checked structurally when using DDPs?
Were footings set?
Checked.
Yes, absolutely. And in many cases like this, we designed the footings as well as the foundations, and that is just you know, a lot of times you don't know how much stress concentration you're going to, I mean, you can calculate, but there's a question about stress concentration under a footings. So we kind of like to design the footings also and maybe have a little hedge against stress concentration. So they were not typical shallow foundations that you would put on just ground that was suitable for that kind of bearing pressure. There was a consideration for stress concentration in the area of those elements.
Excellent. We had another question come in. Would piles installed in a sand layer have been more effective for liquefaction mitigation in comparison to saturated silts?
Yes. Saturated silts, as I said, have broken my heart many times because I went into this process thinking that if you did a CPT and a liquefaction analysis, that if the material showed to be liquefiable, then it automatically was improvable by displacement methods. Not the case. The saturated silts just don't respond very well. That is not to say that somewhere in the United States there is not a saturated silt that will respond, but the history has been not good in terms of getting a response from saturated silts that would move those materials from liquefiable to in excess of a factor of safety of 1. And we've in California, in Kentucky, in a variety of situations, it has been consistent that those silts simply don't respond to displacement.
Great. Another question is, when you were speaking about the 12-inch piles that broke, how was the ground being excavated? Was it by hand or equipment?
Not by equipment. And we, you know, it was a bit of a learning process, but we just found that you could, as careful as you could be, the 12-inch piles were just too delicate to stand up under normal. I mean, we couldn't, it really wasn't practical to hand excavate. I mean, this was a fairly large project, and hand excavating the last foot or whatever to prevent the piles from breaking would have been disastrous. So we just, and it's amazing the difference in the toughness of the 16-inch and the 12-inch piles, but the 12-inch just didn't hold up.
All right, we have 2 more questions here for you. One question is, how is the thickness of the load transfer platform determined above where the elements lie?
Okay. We have a set of design criteria, and it is a function of what we think. You know, when you do this, there is some load distribution between the soil and the elements. Initially, the elements are going to probably take most of the load until you can mobilize the soil. So that is really what governs the load transfer platform. And we have done concrete load transfer platforms, geogrid reinforced load transfer platforms. There is a design process that you go through to determine that thickness based on the diameter of the piles and the extent to which you believe that the load will be concentrated on those elements at the beginning.
Okay, and the next question we have here that actually came in is, it reads, the strength of the grout at the upper part of the pile is different between conventional auger cast piles and drill displacement because of how the processes finish up at grade. So is there likelihood of necking at the upper part of a drill displacement pile in comparison to an auger cast pile?
No, if it's done properly. And I'll share with you some uncomfortable experience. When we first started with this process, if you look back at, I'm sorry, I have wrecked the process here. If I could get down to one of the installation records. Okay, if you look at this record and look at the grout pressure trace, you can see he gets to the bottom, they start pumping grout, the grout pressure goes up, and then it stays, in a fairly comfortable range. And remember, this is the grout pressure 60 or 80 feet above the level of the tooling. It's being read at the top of the tooling. And then at some point, the grout starts to exit around the tool as the tool is being withdrawn. If when the operator sees that grout start to exit, he withdraws the tool more quickly, then there is a possibility of necking in the upper part of that pile. So what the operator should do, regardless of when he sees grout exit from around that tool, is continue to pull at a consistent rate in order to make sure that that pile is filled. And you can see with the red trace, that's exactly what he did. Even though the grout pressure dropped to 0, which means the grout was probably coming out of the ground around the tool, the operator did not speed up the withdrawal process. So it's a legitimate question, and the answer is it's taken care of by prudent operator procedure.
Excellent. And there's one final question, so we'll stop it after this question here. And we appreciate your time of fielding these questions, Willie. What is the typical plastic index values for the saturated silt that couldn't be densified?
Okay, here's the hard part. Some of them are non-plastic. And that was, again, another heartbreak for me, because I figured silts, non-plastic silts, they're going to be fine. They were not. So that is going to be a geology specific issue, but my basic operating position right now is if I am dealing with saturated silts, I am not going to expect anything out of them in terms of densification from the displacement process. And somewhere in the United States, somebody probably knows that they have saturated silts that respond to displacement. I can't point you to where that is.
All right, we do have one more question. We will have this last question, and then in recognition of the time that we have for the evening, I'm sure Willie would love to answer all these questions, but we don't want to keep them for too long here. So this will be the final question that we're going to ask. How meaningful is the grout factor while measuring all the other parameters?
On the displacement system, I assume that we're talking about the displacement system. That's one of the things that was a big adjustment when moving from conventional auger piles to displacement piles. The grout factor in auger piles, we actually don't install displacement piles to a specific grout factor. It's pressure that is the determining factor. And the working concept is, as long as there is positive pressure measured by this system, again, 60 or 80 feet above the tooling, then that, that pile has been filled. We do measure grout factor, but we do not cast displacement systems based on grout factor, which is the way you would cast a conventional auger pile system.
Well, thank you so much, everyone, for attending. Willie, on behalf of the ASCE Geo Institute, I really want to extend our appreciation for the time that you spent with us this evening. It was extremely informative, and it was a topic that I know a lot of the people that participated this evening took a lot out from. Normally in this part of the in-person presentation, we extend our gratitude with a crystal apple, the apple representing New York City. So what we will be doing for Willie is sending him our traditional crystal apple denoting today's presentation and the date, and in recognition for his efforts that he did for us this evening. So Willie, again, I want to thank you. I want to thank DFI Traveling Lecture for what they've helped to participate to put this together, and everybody that was able to join us this evening. We had a very nice turnout. New York always has a very strong participation, and for anyone that was familiarized with DFI, it's a great organization along with ASCE. We do have a lot of joint presentations together, and please look out for things both from ASCE and DFI in the future. So Willie, thank you again, and Mary Ellen and everybody else from DFI.
Thank you, Mike. Hopefully we can do it in person next time.
Excellent. And everybody else, that concludes our proceedings for this evening. Thank you so much for your participations, and your questions were very insightful. So have a good night, everyone.